This is the second video in the Surface Mount Rework series. In this videotape, we're going to examine the tools and techniques for removing and replacing chip components. There are several types of surface mount chip components that we'll be working with. We'll begin by looking at each of these types. Then we'll explain the terminology, as well as any special precautions you'll need to be aware of during the removal and replacement operations. Let's start now with chip resistors. These are a very common component style. The component body is made from alumina, which is an extremely hard, white-colored material. The resistive material is normally located on the top. Chip resistors are usually mounted with the resistive element facing upwards to help dissipate heat during circuit operation and for identification purposes. The metallized terminations on the ends of the resistor chip will typically wrap around three sides of the component. Chip resistors come in several different sizes. While some of them are relatively large, the trend is to use smaller components in today's surface mount designs. Their size is described by a 4-digit number, for example, 08, 05. The first two numbers represent the length of the component. In this case, 0.08 inches. The last two digits represent the width of the component, 0.05 inches. Each component will also have a metric size code, based on millimeters rather than inches. 2012 is the metric equivalent of the 0805 chip component. The first two digits, or 20, would equal 2.0 millimeters in length. The 12 represents 1.2 millimeters in width. Another style of chip components is the ceramic capacitor. These components are constructed of several layers of ceramic with internal metallized layers. Because metal heats up much faster than ceramic, these ceramic capacitors need to be heated slowly to avoid internal separations between the ceramic and metal layers. This internal damage will generally not be visible, since any cracks will be inside the ceramic body of the component. In some cases, a crack may be so small that the damaged component will function properly for a while, but the heating and cooling caused by turning the product on and off will cause the component to expand and contract. This may eventually cause the separation to grow to the point where the component will fail. This is why we need to avoid rapid heating of ceramic chip capacitors during the soldering operation. Ceramic chip capacitors will require gradual heating methods, which we will explain later in this tape. Another style of chip component has a molded plastic body that protects the internal circuitry. There are a number of different types of components that share this type of exterior package, including tantalum capacitors, inductors, and potentiometers. If you would like more information on the function of these components, you can refer to the IPC videotape on component identification. The termination styles for plastic chip component packages also varies considerably. Tantalum capacitors will often have a wraparound termination, starting on the outside end and bending around the bottom of the component. Some of the inductors will have terminations that extend out to the end but are mainly underneath the component body. Finally, there are some potentiometers with leads that extend away from the body. One other style of component that we will be discussing is the MELF, or metal electrode face cylindrical components. There are capacitors, resistors, and diodes in this MELF style. It can be hard to tell them apart, since there is no universal coloring or component designators printed on the component bodies. While all of these components certainly look different, they are relatively similar as far as removal and replacement techniques, with the exception of ceramic chip capacitors. We will be working with different component types as we explain each of the various removal and replacement techniques. Whenever there is a specific concern relative to a particular style of component, we'll make sure to cover that information. It's also important to always follow the safety requirements to protect both yourself and the assemblies that you work on. There are separate IPC training videos on operator safety and ESD control. If you haven't already received training in these areas, we recommend that you review both of these videos before you begin using the tools and techniques described in this tape. Now let's talk about our first rework tool, the continuously heated hand soldering iron. There are a variety of interchangeable single point tips available for specific soldering applications. Here are some of the basic tip shapes and terminology that we'll be using. Chisel tips are basically shaped like a chisel. The flat section of the tip has a lot of surface area, which helps to transfer the heat quickly. Conical tips also resemble their name. Conical tips also come in extremely small sizes for micro-miniature applications. Bifurcated or forked tips are also useful for chip component rework. Forked tips come in several sizes to accommodate many of the different styles and sizes of chip components. The size and shape of the tip will also have a significant effect on the rate of heat transfer. Larger tips with more surface area will transfer heat much faster than smaller tips. Tip selection will be based on the size of the component. While there is no exact rule about how the size of a single point tip should compare to the size of the termination, it's obvious that if the tip extends too far beyond the edge of the joint, it could come in contact with another component or the surface of the board. A burned area around conductor traces or lands can reduce the adhesion between the metal and the laminate surface. This can result in a lifted land or conductor trace. To avoid this problem, the width of a single point tip should be slightly smaller than the width of the land. We'll be recommending a specific tip as we explain each rework technique. But let's stop now and review the information we just covered on component types and soldering tips. Now let's discuss chip component removal using a continuously heated hand soldering iron. It is possible to remove a chip component with a single soldering iron by moving the tip back and forth in order to melt both solder joints at once, then flicking the component off the lands while both joints are still molten. Perhaps the reason that this method is ever used is that it doesn't require any special tools. There are some major disadvantages with this technique. For example, as the component is pushed away from the lands, it can lodge against another component. As the molten solder solidifies, the component will be resoldered to the other component. This type of removal operation can also leave a stream of solder on the board. Depending on where this solder ends up, it can create additional problems. The amount of heat needed to keep both solder joints melted simultaneously can also weaken the adhesion of the land onto the surface of the board. If the iron starts to push on one side of the component as the opposite solder joint begins to solidify, the pressure can cause the land to separate from the circuit board. Some technicians use two soldering irons to remove chip components. This technique can overcome some of the problems we just mentioned, but it does take considerable skill to properly align both tips without touching anything else. The first recommended method for removing chip components uses a bifurcated or forked tip with a hand soldering iron. Forked tips are designed to fit over the top of chip components and to reflow both solder joints at once. There are different sizes of forked tips to fit the various types and sizes of chip components. The ends of the forked tip fit over the component with just a slight amount of extra space for solder. Learning which components fit into specific tips takes experience. Before we begin the tip preparation process, we need to apply flux to the solder joints. In this case, the flux will help remove oxidation and transfer the heat between the tip and the solder. We always want to flux the component before we prepare the tip. so that the clean tip doesn't have to wait around and oxidize while we perform the fluxing operation. The type of flux will depend on your company's cleaning procedures. Almost any type of flux will work. The key is compatibility with your cleaning procedures and chemistry. There are also no-clean fluxes that are becoming popular. As the name implies, these fluxes do not require cleaning after the soldering operation is complete. Now we're ready to prepare the tip. Since this particular tip has a cavity, it will require special cleaning and tinning procedures. First, we'll need to remove any solder from inside the cavity of the heated tip with a non-abrasive fiber tool. It's important never to use a wire brush for any tip cleaning procedure, since the wire will scratch all the way down to the base metal. This would allow oxidation to form on the base metal and severely decrease the useful life of the tip. After cleaning the tip with the fiber tool, the next step is to remove any oxidized solder by shocking the tip on a wet sponge. Now it's time to add solder to the properly cleaned tip. We need to fill up the cavity until there's a small crown of solder that reaches from one side of the tip to the other. Knowing exactly how much solder to add is also learned by experience. We want enough solder to help transfer the heat quickly, but not enough to fall out of the tip during use. The solder will also provide surface tension to lift the component off the lands after reflow. Since the tip has more metal surface area than the lands on the circuit board, the solder will be drawn toward the metal tip, and so will the component. Fork tips can be used to remove a number of different styles of chip components, as long as they fit properly in the cavity. At this point, some of the extremely small chip components won't fit into any of the fork tip sizes that are presently available. To remove these tiny components, you can use a 1/16 inch chisel tip to simulate the fork tip removal process. We need the tip to be slightly wider than the length of the component so that it reaches almost to the end of both lands. The first step is to flux the component to enhance the heat transfer process. After we clean the tip, we'll apply a little bit more solder than you would normally use to tin the tip. Then we'll place the soldering iron at an angle so that the tip lies flat against the top of the component. We'll use the extra solder on the tip to melt both of the solder joints simultaneously. The flat side of the soldering tip has more surface area than the edge of the tip. This additional surface area will help to create the necessary surface tension to lift and hold the component. This technique will only work for the smallest chip components when properly sized bifurcated tips are not available. Adding the right amount of solder to the tip will also take some experience. If you add too much solder, especially when the components are tightly spaced, you could end up with solder bridging. Now let's cover the removal of chip components that are bonded onto the board prior to the original soldering operation. A small dot of adhesive is often used to hold chip components in position during the wave soldering process. Typically, these chips will be located on the bottom side of the circuit board that has through-hole components located on the other side. This way, the through-hole leads and the chip components can be wave soldered in a single pass. Whenever you see a board like this, you can generally assume that the chip components have been bonded onto the board. To remove these chips, we'll have to apply enough heat through the component body to soften the bond. The bifurcated tip is the simplest tool for removing adhesive bonded chip components. After we prepare and pre-fill the cavity with solder as usual, the tip is then applied to the component. You'll need to leave the tip on the component for 1 or 2 seconds after the solder joints are melted in order to transfer enough heat to overcure or soften the adhesive. Now take a wooden stick or curved tweezers and push the component sideways until the bond finally gives way. Some adhesives will loosen up quickly, while others can be a lot more difficult. Let's take another break here to review chip removal procedures using forked tips. In this next section, we're going to cover land preparation prior to component replacement. Before we replace any type of surface mount component, it's always best to remove any remaining solder so that it does not become part of the new solder connection. Remember that when the component was removed, some of the original solder will still remain attached to the land. That solder has already been heated twice. If it becomes part of the new solder joint, it will have been heated at least 3, possibly even 4 times. We all know how food gets a little crustier every time it's reheated. Reheating solder, even with the addition of flux, can also affect the physical composition of the metals. Every time that solder is reheated to its melting point, or even close, the molecular structure tends to become increasingly brittle. We need the solder to be soft or ductile in order to absorb the stress of expansion and contraction caused by the heating and cooling of the circuitry. That's why it's best to remove all of the old solder from the lands and replace it with fresh solder whenever a component is reattached. There are 2 techniques for preparing surface mount lands, depending on the type of equipment you have available. The first method uses a solder removal braid. Solder braid comes in different widths. We'll want to use one that matches the width of the land or is just slightly smaller. After we place the solder braid over the land, we need to apply heat. The width of the soldering iron tip should also match the width of the land. If the tip is too large for the braid, it will hang over the edges and could potentially burn the board. If the tip is too small, it will take much longer to heat up the braid. Remember that we want to apply heat for the shortest possible time to avoid thermal damage. After we have selected the proper tip and braid size for the land, the application of an external flux is optional. Most solder removal braid already comes with a powdered flux inside the copper strands, which is melted and activated by the heat of the iron. Adding additional flux will help to transfer the heat even faster and also help improve the wicking or capillary action of the copper braid. As you apply the heat, it's important to avoid putting any downward or sideways pressure on the land. Since the adhesive resin underneath the land is being heated at the same time, the bond between the board and the land will be at its weakest. Sideways pressure can also scrape the land right off the board. Downward pressure can result in a bowed land or an extremely weak bond. The weight of the iron should apply sufficient contact to quickly heat the solder braid. The heat that passes through the braid should melt any solder that remains on the land within a few seconds. The wicking action of the copper braid will draw the solder away from the land. This wicking action should be visible. When the wicking stops, it's time to remove the braid and the iron. The used portion of the braid should be clipped off, and the other land should now be prepared exactly like the first. After the excess solder is removed from both lands, we're ready to reinstall the replacement component. The second land preparation technique uses a vacuum extractor to remove the used solder. The solder extractor has a heated tip with a hole in the center to vacuum the melted solder away. There are different tip sizes depending on the size of the job. Once again, the diameter of the tip should match the width of the land. This is the optimum vacuum tip size. A larger tip would extend over the edge of the land and could potentially burn the board. For this particular operation, the application of flux is optional. Now the heated tip is placed onto the land until you feel the solder melt and the tip drop. Again, it's important not to use any downward or sideways pressure on the land. The weight of the handpiece is sufficient. After the solder melts, the operator activates the vacuum, and the solder is sucked through the hole in the tip into a solder storage chamber. It should only take a second or two for all of the solder to be removed. After the solder is vacuumed from the land, the tool is lifted away. Remember to allow the vacuum to continue for an additional few seconds to make sure that the solder has had enough time to travel through the tip into the storage chamber. After we remove the flux residue, we're ready to install the component. Let's stop once more to discuss any questions you have on land preparation for chip components.